All right, welcome back. So this is going to be section 2 on rate laws and rate constants. We're going to use the first method of determining rates in this particular case. The first thing to talk about, though, is how to write a rate law, because we haven't seen that prior to now. So rate laws are usually expressed by this equation that you see up here. Rate equals K is always the start of a rate law. Then we multiply times a bracketed concentration represented here by an A, and this is the reaction that we're represented, to some coefficient, to some exponent times the coefficient of B to some exponent, times the concentration of B to some exponent. X and Y are going to refer to what we call reactant orders, and we're going to study this on the next page, but usually orders are 0, 1, or 2 in the case of chemical reactions. Anything beyond a second order is usually considered very complicated, and there's a little bit more of a discussion on that later on in this chapter, but for our particular purposes, most rate laws are going to have exponents of a 0, 1, or a 2. You'll also notice that 0, raise anything to the power of 0, and it becomes 1. So 0 order reactants usually don't make it into our rate laws. Okay? In this particular case, we're using the example of NH4 plus and NO2 minus. One of the things I want to double check real quick. I want to make sure. Okay, so for some reason, this is not showing what it should. In fact, this reaction should say A plus B makes C. Rate laws usually only have reactants in them. Okay, they only have reactants in them. It makes sense because we're using the order of a reaction related to the reactants for each of the different things up here. In this particular case, the example they're showing you is actually these two things are being added together. The total order of the reaction, so each one is shown in this rate law. Each one is shown to have a first order. So for instance, NH4 plus, there's a fictional 1 here, and NO2 minus also has a fictional 1 here. Because they have those fictional exponents, we know that they each have an order of 1, and we know that the total order is just, in order to find the order of a reaction, the total reaction, overall reaction order, you just add the two together. So for instance, this 1 plus this 1 makes 2. The overall reaction is second order in this particular case. Now, the next couple of things we're going to be looking at is how do we determine how something is first order, second order, or 0 order. That is the part of the rate law stuff that gets really complicated, and there are multiple methods, and that's what we're talking about when we say that there are methods for determining the rates. The first method that we're going to talk about that does not exist is related to stoichiometry. Just because a reaction has stoichiometry does not mean that its rate law is going to be related to its stoichiometry. So in this particular example up here, you have a 2 in front of the N2O5, but the rate law has it being first order. Remember, the 1s are not going to be there. If it's a 0, it's not shown. Okay, so in this particular case, the rate order of this reaction is first order with respect to N2O5 and overall first order. That's what we say. But that doesn't match the stoichiometry that we're given, and that's okay. They're not supposed to. Sometimes that might happen, sometimes it might not. So look at our second one, right? Our H2 reactant and our I2 reactant both have 1s in front of their coefficients, and coincidentally, they also experimentally show a rate order of 1 for each, meaning an overall order. So I'm going to do overall order just to practice with you over here. Overall order, remember, you add them together. So this one is 1, and this one is 1 plus 1, 2. Okay, now we go down to our next one, and we have a 1 here, and then this one has a 1/2, which is so weird, but it can happen. So when we add them together, it's going to be 1.5. Okay, but again, looking at your rate law here and relating it back to your stoichiometric coefficients, notice the CH3C or the CHCl3 has a 1 in front of it as a stoichiometry, but the Cl2 does not have a coefficient of 1/2. So again, stoichiometry does not necessarily determine rate laws here. That's the first big takeaway in this section. All right, next thing is to talk about that K value. So remember, all rate laws start with rate equals K. Then you add something after, and that's usually the experimentally determined or determined using information that we'll find later. In this case, we want to talk about this K value. So we're focusing on that rate constant. Just because the word constant is in it doesn't mean it will always be the same value. In fact, rate constants are reaction dependent. And I don't mean reaction dependent like, oh, you're adding H2 plus I2 to make HI. I mean concentration and reaction dependent. So if I start with a specific reaction, I may have a different rate than if I started with lower reaction concentrations. And so that part of this is going to be something to kind of hold on to for a little while here. Our rate constants also are going to have different units depending on their orders. So if something is 0 order overall, it's going to have a rate constant unit of concentration times inverse seconds. If it's first order overall, it's going to have inverse seconds. If it's second order overall, it's inverse molarity inverse seconds. So kind of star this, put it in your notes, write it down, box it, put it away for later, okay? Put this away for later, put this aside. But do understand that the magnitude of K does matter. So if we have really, really big numbers, we say that high reaction rate constants equal fast reactions. Small reaction rate constants then are considered common for slower reactions. Okay? Okay, so our first method is to use initial rates of reactions to determine rate laws. Okay? You'll see this like weirdly described equation. Okay? We're going to talk about how to use that by following an example. The example that we're trying to determine is what is the rate law, including orders for each of the reactants in a reaction that have NO2 and NH4+. In order to do this, we need data, okay? But I want to make sure we see concentration ratio raised to an exponent must equal rate ratio. That is the first equation that you need to pay attention to here. And it's more of a relation than it is anything else, okay? So here's the data, okay? The first 3 experiments they define as being able to be used to determine how NH4, the change in concentrations, initial concentrations of NH4, affect the rate of the reaction. The last 3 experiments are going to be all about NO2 minus. Okay? When we're looking at these tables of data, please understand that we are looking specifically for, you're not always going to be given data that's super beautiful. You have 6 equations. You can play with it however you want. You may be given only 4, and we're going to walk through how to do this. So if we're trying to determine how, say, reactant NH4+ affects the rate of a reaction, then we want to focus on experiments where the other reactant is held constant. So notice these are all the same. These are constant for these first 3 experiments. So we're not going to look at this data. This data is not useful to us for this particular part of the experiment. Okay? What we are going to look at is how NH4 changes between, say, experiment 1 and experiment 2. We know it goes up by a factor of 2. Then we're going to compare that to how the observed rate changes. From experiment 1 to experiment 2, we see that the initial rate doubled. Okay, so remember that was concentration. So I'm going to go back to that previous slide. We're going to use this particular information. Concentration ratio raised to some exponent equals rate ratio. The exponent is our goal. So concentration ratio, aka double, so 2 raised to some variable we don't know is going to equal the rate ratio, in this case 2. And this is for NH4. Oops, I'll do this up here. Okay, so again, concentration ratio raised to some exponent equals rate ratio. Okay, so for NH4 plus, we know that this was the concentration ratio doubled, so 2 to some number equals 2. So that's our concentration versus blah, blah, blah. Okay, that exponent then, x, has to equal what in order for this to occur? The answer is 1. Okay, now could we use, say, experiments 2 and 3? Absolutely. We want it to go from here to here. We know it also doubles. We want to go from here to here. We know it doubles. Again, we kept all of these the same. That's why we can actually ignore NO2 altogether. So make sure you're doing that. If these two are the same, you can compare these. Okay? All right, moving on to NH4. Moving on from NH4. Now we're going to look at NO2. Notice that for these 3 experiments focused on NO2 minus, these 3 are all constant. Again, your data is not always going to be as beautiful as this, but you're always looking for this one to not change if you're wanting to analyze this one. Okay? You're always looking at, say, for instance, NO2 to change, but NH4 to stay the same, or NH4 to change, but NO2 to stay the same. Think of this as like A and B. Typically, we're only ever comparing 2 reactants. In scenarios where there's only 1 reactant, it's a little bit easier to find. But in this particular case, understand that A and B are being compared. Okay? All right, so from trial 4 to trial 5, or experiment number 4 to experiment number 5, the concentration doubles and the rate also doubles. So again, for NO2, the concentration ratio is 2 to some number we don't know, that's our exponent, and then our rate ratio is 2. So y in this case must also be 1. Now this tracks from like a previous slide where we saw NO2 was first order and NH4 was also first order, and the sum of them is going to be 2. In this particular case, you kind of see how the math breaks down. As far as NH4 is concerned, as NH4 doubles, the rate doubles, and as a result, you know the exponent is 1. Same thing for NO2, as the rate of concentration doubles, the rate doubles as well, which means our final reaction rate is going to be an exponent of 1 for each reactant. And then from there, if we wanted to find K, we're going to substitute the value in from one of the experiments. So let's go back and figure out. So this is 5.4 times 10 to the negative 7. Concentrations at 0.01 and 0.2 molar. So they used this first experiment. Once they had a rate law, they used this first experiment's data, including the rate and the 2 initial concentrations, raised to the 2 powers we just found, to find K. Okay, so this is all data from that first experiment that they took. They plugged it in and they found that the rate, constant K, is this guy. Okay, then for posterity's sake, they showed you what this would look like if you were actually trying to put a rate law together that had a value for K instead of just a letter K. Okay, now from here, for equations like this, I could ask you things like, okay, what would the concentration of NO2 need to be if I started with a concentration of blank for NH4 and the rate is blank? Or what would the rate of the reaction be if I started with initial concentrations of NH4 at 0.1 molar and NO2 at 0.7 molar? Right? So if I wanted to, I could plug in some what if type information in order to determine what the reaction rate would be under other conditions, or I could find what the rate is, or I could find what the concentration would need to be for something if I was given a rate and one of the other concentrations. Okay? All right. Well, that is the end of section 2 for now. We will talk about another method of determining rate laws and using rate laws in our next section.